A quadrilateral with all sides equal is a parallelogram. Now this theorem is true. We will see later that its converse is not true. Before doing that, I will prove this theorem. So a quadrilateral is a four-sided figure. This quadrilateral has all four sides equal. We are going to prove that this is a parallelogram. Of course, it looks like a parallelogram, but you know, looks can be deceptive, so we need to prove that it's a parallelogram by proving that opposite sides of it are parallel. So we want to prove that this line is parallel to this line, and that this line here is parallel to this line here. To prove this, we draw in a diagonal. Now there are two triangles formed, and we note that the sides of both triangles are the same. This side here is equal to this side here of the second triangle, and this side here of the first triangle equals this side of the second triangle. And also, of course, they have this side in common. So the three sides of both of these triangles are the same. So by the Sss condition for congruency, the triangles are congruent. So Sss stands for the three sides the same in both triangles. Now let's look to corresponding sides of both of these triangles. Let's take the angle that's opposite this side here. I'll call it A. Well, the side corresponding to this side in the other triangle is this side. Actually, we have a choice. We could also say it's this side, because these two sides are equal to this side. But anyway, if we work with this side, the angle that's opposite this side is up here. So these angles must be equal, because they're opposite the same side, the side of the same length in both congruent triangles. Now, if I call this line L and this line M, since A is equal to B, we have what are called alternate or Z angles because of this Z shape. And if two lines are parallel, then these two angles are equal. And the converse of that is also true, actually. I didn't state the converse of it, but it happens to be true. If these two angles are the same, then this line is parallel to this line. Now this angle here, which I'm calling C, is equal to B, because C and B are angles in this isosceles triangle. This side equals this side. So the angles opposite the equal sides are equal to each other. C and B are opposite these two sides. And of course both B is equal to A. So these three angles are the same. Actually, we can also say A is equal to D, for the same reason. If we look at this second isosceles triangle. So these four angles are equal to each other. So I'll just call them all angle A. Notice that we get another pair of alternate angles here. If we look at this Z shape, these two angles are equal to each other. And if they're equal, it means that this line is parallel to this line here. I'll call this line R and this line S. So in a similar way to how we prove that L is parallel to M, we see that R is parallel to S just by stating that these two angles are equal. So that's just the converse of the notion of alternate angles. Two lines are parallel, then these two angles made are equal. If these two angles made are equal, then the lines are parallel. So we've shown that opposite sides of this quadrilateral are parallel. So that means that this quadrilateral is a parallelogram. Now the premise of the theorem is that we have a quadrilateral with all sides equal. So that's what's given. And from that we concluded that such a quadrilateral is a parallelogram. So here's the premise and here's the conclusion. Now the converse of the theorem starts with the conclusion of the theorem, which is we are given a parallelogram, and we want to deduce the premise of the theorem, which is that the parallelogram is a quadrilateral with all sides equal. Well, a parallelogram is a quadrilateral, so we don't have to prove that, but we need to prove that all sides are equal. So for the converse of a theorem, we reverse the roles of premise and conclusion. The conclusion of the theorem becomes the premise of the converse, and the premise of the theorem becomes the conclusion of the converse. Now it's very easy to see that this is false. Here is a rough sketch of a parallelogram. Opposite sides are parallel, but notice that it doesn't have all sides equal. This side equals this side, but this side here is certainly not equal to this side here. So the converse of this theorem is false. We just need one counter example. We need to just construct one parallelogram that violates this.